Let's work through two examples where we are going to find the general antiderivative of each function given. So our first function, f of x equals 3x to the fifth minus 2x cubed plus 5x minus 1. So we'll go ahead and use capital F of x to represent the antiderivative. And this first term has a coefficient of a 3, so I'm just going to leave the 3 out in front. And now we're going to work on trying to compute the antiderivative of just the x to the fifth portion. So remember, this is essentially the derivative, and we're trying to work backwards to figure out where did this derivative come from. So since this is an x to the fifth power, if I were to add 1 to the exponent, I would end up having an x to the sixth power. Now if I do just a quick little check here in my head, I'll actually write it down, you don't need to, but if I were to check x to the sixth, the derivative of x to the sixth would be 6x to the fifth. So I would get the x to the fifth that I want, but I would end up with this extra multiplication by 6 that I don't want. So to think about undoing that multiplication by 6, we could divide by 6, which would be the same as multiplying by a 1/6 in this case. So now, if you check the derivative of 1/6 x to the sixth, the 1/6 would stay in front, the derivative of x to the sixth would be 6x to the fifth, and see, by having that 1/6 as your coefficient, that's going to multiply by 6 and equal 1, and now you are going to be left with just x to the fifth, which is what we wanted. So we've essentially worked backwards. We've said that the antiderivative of x to the fifth is 1/6 x to the sixth. Let's work on our second term in the same way. So we have a minus 2. I'm just going to leave that out in front as a coefficient, and let's work on computing the antiderivative of x to the third power. So again, if it's raised to the third power and we're looking for the antiderivative, then we know a cubic, an x to the third, had to come from an x to the fourth power, because we're essentially adding 1 to the exponent. If I were to check, the derivative of x to the fourth would be 4x cubed. I'd end up with this multiplication by 4 that I don't want. So to undo that multiplication, I'll multiply by 1/4, which is the same as dividing by 4. So multiplying by 1/4 is essentially going to get rid of that 4 that we would have in the derivative. So therefore, the derivative of 1/4 x to the fourth would just be the x cubed, which is what we're looking for. Let's try our next term. Once again, we have a positive 5x, and 5 is my coefficient, so let's just leave the 5 and work on the antiderivative of x. Now that's right now x to the first power, so if I add 1 to the exponent, I know that had to come from an x squared. Again, if you check the derivative of x squared, you'd have 2x to the first power. We don't want a 2, so therefore we will divide by 2, which is the same as multiplying by 1/2. And then lastly, we have a minus 1 there. At the very end here, we have this minus 1, which is a constant. So it must have come from a minus 1x. And if you want to think about a constant like -1, it really has an x attached to it, but it's x to the 0 power. So if you think about adding 1, if you were wanting to use the same procedure we did on the previous terms, if you added 1 to the exponent, then you can see that is where we get the x to the first power. Sure enough, the derivative of x to the first power is just going to be 1. So in this case, the derivative of -1x, when we're checking, the derivative of -1x is just -1. Of course, we typically don't write the -1 in front of the x, so we would just write this as -x. So let's simplify everything that we have here so far for our antiderivative. So big F of x, if we go ahead and multiply, 3 times 1/6 will give us 1/2 x to the sixth, minus 2 times 1/4 is 1/2 x to the fourth, plus 5/2 x squared, minus x. But then remember, because we're finding the general antiderivative, we want all of the possibilities, which means we recognize that we could add a constant, any constant value, because the derivative of a constant will be 0. So this is what I have right now for my general antiderivative, but of course I want to be sure I'm doing this correctly, so it's good to do a check. And I recommend that you check your first few, and then as you get going, you'll be doing the check mostly in your head. So we're going to check this antiderivative by computing the derivative of this and seeing if we get the original function. So if we compute the derivative of 1/2 x to the 6th, 6 times 1/2 will give us 3, and then we'll subtract 1 from our power, so that will be 3x to the 5th, minus 4 times 1/2 will be 2, so that's 2x to the 3rd, plus 2 times 5/2 will be 5, so that'll just be 5x. The derivative of negative x is -1, and then the derivative of the constant is just 0. And sure enough, look at the expression we have here and how it matches the original. So this tells us that our antiderivative is correct. Now let's use a similar procedure for this second example. We have f of x equals 3e to the x plus x to the 4th minus 4x cubed plus 3x. So again, I'm going to use capital F of x for my antiderivative. My first term is 3e to the x, so the 3 is my coefficient. And the antiderivative of e to the x is just going to be e to the x. My second term is a positive x to the 4th. So if I add 1 to my exponent, that will give me an x to the 5th. But again, I don't want to end up with a 5 in front as my coefficient, so I'll divide by 5, which is the same as multiplying by 1/5. Some people prefer to write this as just x to the 5th over 5, and of course that's fine. I just choose to go ahead and write it as a fraction, coefficient. Alright, my next term is -4x cubed, so I will leave that -4, and I will work on the antiderivative of just the x cubed. So if I add 1 to the power, I realize that that will leave me with an x to the 4th power. And then if you were to say, well, I don't want the 4 in front that I would end up with, so I would essentially divide by that 4, so that would leave me with a 1/4 there. So 1/4 x to the 4th is the antiderivative of just the x cubed part. And then my last term is a positive 3x. That's really 3x to the 1st power. So I'm going to have to fit it down here, sorry. My coefficient is a 3. If I were to add 1 to my exponent, then that would mean I would have an x squared. But I don't want to end up with a 2 in front, so I'll multiply by 1/2. And then remember, this is a general antiderivative, so sometimes it's important to put it at this step rather than at the very end, because you don't want to forget that constant at the end. So let's go ahead and simplify. We're going to end up here with 3e to the x power plus 1/5 x to the 5th power. -4 times 1/4 will just be a -1, so a negative x to the 4th, plus a 3/2 x squared, plus a constant. So this is my general antiderivative, which of course, since it's only our second one, we want to check this. Once again, the check can really be happening in your head as you move forward, but it's important to find the derivative to be sure we get the original function here. So the derivative of 3e to the x will be 3e to the x. Then we would have the derivative of 1/5 x to the 5th. So the 5 will come in front and be multiplied by the 1/5. That would just get me 1 for my coefficient. So that would be 1x to the 4th. The derivative of negative x to the 4th is going to be a -4x to the 3rd. We have 3/2 x squared, so the 2 will come in front and be multiplied by the 3/2, which would leave us with a 3x to the 1st power, and then the derivative of a constant will be 0. So once again, we notice that when we computed the derivative, this was indeed the same as the original function that we were given, and this tells us that our antiderivative is correct. So let's go ahead and generalize the process that we've used on these previous two examples. These have been examples primarily with terms that had powers, x raised to a power. So if we are basically given a power function, a term that has x raised to the power, and we're trying to work backwards, it's like we're undoing the power rule that we used to use for derivatives. So some people call this the power rule for antiderivatives. So when we're finding the general antiderivative of x to the n power, then we are going to add 1 to our exponent. So we'll have x raised to the n plus 1 power. And then whatever that new exponent is, that's what we want to divide by. So I'm going to write it as 1 over n plus 1 as my coefficient. So this is our general antiderivative of x to the n. To make it a general antiderivative, we'll put a plus c there. And if you prefer, some textbooks and some people, again, write this as division instead of a fraction. So if you'd rather write it as x to the n plus 1 divided by n plus 1, of course that would be acceptable too. Those are interchangeable. So this is kind of our generalization for our procedure for finding antiderivatives when we have power functions.